So today was going to be on pipeline processors, but after 2 takes, I realized I need to explain sequential circuits to comfortably explain pipeline processors. So I'm going to do that. I know this is like a basic topic in architecture, but it's pretty foundational in my opinion. It's one of the big like paradigm shifts, especially when you're writing RTL compared to coding. And one could argue that having an understanding of like an incredibly complex architecture topic, like some high level instruction level parallelism, out of order processing, whatever stuff, requires a deep understanding of pipeline and sequential circuits. Therefore, pipeline and sequential circuits are an advanced architecture topic. Seems paradoxical. Anyways, so we're gonna start off thinking why sequential circuits. It's because you don't have any memory. Like, just look at this. Like, your inputs toggle, your outputs toggle. Your inputs toggle and you want them to stop toggling, and then you want your outputs to not toggle and store the last inputs, but you can't. You don't have state. You don't have memory. So, we could quickly... English is bad today, but I'm not an English major. We quickly solve this with the SR latch. The SR latch is a set reset latch, so when R is low, set goes high, our output becomes high. When S goes low, our output stays high because there's memory now, yay. When R goes high, our output goes back down to low, and then when R goes low, our output stays low. This is quite awesome. And then when R and S are both low, it holds, but when R and S are both high, you have an illegal input. And you have, I know this is 0 here, but it's actually like metastable, XXX, and it's like really bad. This is way better cold. I had one warm and I didn't like it as much. So that's why latch is cool, but like, you know, the whole illegal input thing, and like you gotta set, then you gotta reset, and it's level triggered, and it's just so much work. So we very quickly transition to the D flip-flop. The D flip-flop, you might notice, if you have a very, very keen eye, that the layout of having a sort of latch-like structure here is still the same. But now we have this logic in front of it. What this logic is doing is to basically gates our latch based off of a rising edge of a clock. So it's kind of like a spaceship. And when you have those spaceship doors where like you don't want to just open the door, a singular door, because then the space rocks go in and the vacuum happens. So you have one door and the dude goes in, then it closes behind him, then you have the other door. This is the first door, this is the second door. And then your memory is like home, and your dude is like the signal. And yeah, there's a D flip-flop. Now we have memory, and it samples your data at a rising clock, and it remembers. This is awesome. 16 transistors. 16 transistors? How many transistors in a NAND gate? Hell yeah, 4 transistors per 16 transistors. I passed that class. So now we have a very brief go at sequential circuits. So now we're going to talk about pipelining. So to talk about pipelining, we'll first talk about some combinational circuits. Some combinational circuits. Some combinational circuits. Combinational circuits. What are we talking about today, guys? We're talking, oh my god, dude, come on. Talking about some combinational circuits. So, let's assume that we have this block of logic. And we have our input, which is coming out of a register, just to ease your minds. And then we have, these can compute in parallel. A takes 5 nanoseconds to complete, B takes 6 nanoseconds to complete, respectively, and then C takes 14 nanoseconds to complete. So our total latency of the circuit, latency being the amount of time between when an input is toggled and then a corresponding output to that input is produced, is going to be 6 plus 14, which is 20 nanoseconds. And then our throughput's like 1 over 20. So now, let's say there are 2 reasons why we might want to pipeline this design. The first is because we want to abuse that instruction level parallelism. When A and B are done computing and hand off to C, they just sit there and do nothing while C crunches. When realistically, if we pipelined it, C can crunch, and A and B can crunch to the next input, hand those over, and now we have some instruction level parallelism going on. The second reason is, let's say this block, like this square we drew here, is actually being placed into a larger design, and the clock of that larger design is 15 nanoseconds. We now have an issue, because assuming our output's registered, our register to register path here is 20 nanoseconds. The prop delay here is 20. But our clock is 15. What this means is some other part of the design is going to put an input in, next cycle, i.e. 15 nanoseconds, is going to check that register, and it's not going to have the right value. So, Bravado isn't actually going to tell you did this wrong. What's going to actually happen is you'll have a black screen, your audio is going to be jumbled, your graphics is bad, your FFT is wrong, your math is wrong, whatever, and you're looking through the Bravado logs thinking, what's going wrong? What did I do wrong? And you see in the logs, assuming your design wasn't touched by place and route at all, WNS, weighted negative slack, is actually negative. This means that you didn't meet timing. This is a very popular issue. This is what people mean when they say my design isn't meeting timing. My design is taking longer, or my longest register to register path is longer than our clock cycle. So there are now malformed input-output calculations, things are going wrong. So the way we fix this, and the way we also incorporate some instruction level parallelism into our design, is we put this right here. We put these flip-flops. This is the flip-flop symbol. Now what's going to happen is A and B get an input, they put the input into the register, and then next cycle, C grabs that, does its crunching, and then hands it off. This is pretty good. Notice how this meets timing, but if we chose any lower value, if we chose lower values, we would end up not meeting timing. If we chose like 13 or 12, this is no longer gonna, not that. If we chose like any lower times for the clock, like 13 or 12, this would take even longer, and we would need to like split this design into different chunks. And that's the hard thing. Like when you're designing, obviously it's super easy at this really high level, but when you go down and like you just make a very centric conversion and it's all in one go, and then you realize, oh, I need to pipeline it because I have a negative WNS. Or you think, oh, how can I start meeting timing? Then it's really annoying, because then you're like, oh, what variables do I have to register? What variables do I not have to register? Oh, there's this bypassing bug. Oh, there's this. Oh, there's that. And everything just goes wrong. But having a very strong understanding of this helps, which is why covering it over and over and over again is actually really helpful. You can pipeline huge designs and then go on to the next one, and it's just very overwhelming to like pick apart a design like this. So breaking it down to letters is actually something I really recommend. So now our latency is, a given latency is no longer going to just be the latency of like you adding it up. It's actually going to be the number of stages your pipeline has times the clock cycle. So our clock cycle is 15 nanoseconds. We have two stages. We have this one and this one. So it's going to take 30 nanoseconds for an output to come out, which is more than 20. But now our throughput is just going to be the clock cycle, because assuming we hit steady state, we'll actually just pump out data every clock. So our throughput just changed to 15 nanoseconds, which is quite better, I think. Probably. Anyways. And yeah, that's what you get out of it, right? You get that instruction level parallelism. You get higher throughput in exchange for there being more latency, because you're splitting it into bigger things. But your design is already taking way too long, so you needed that more latency. The thing we're really losing out on is there's this chunk that we're giving 14 seconds of time to the 6 nanoseconds. So, assuming you weren't trying to work into a bigger design and you were just trying to get this design, a better question would be, how many operations in C can we shift over to B? That way, C can take less time and we can drop our clock. But that depends, right? Because like if you're synthesizing for certain boards, you might have different times and all that. So let's code out these two solutions in Verilog real quick. Nope, I would not. I need to get a frickin'. next? Is it gonna be a previous take? It is. Okay, I'm actually just gonna leave this. So here, let's say our C is gonna be this multiplication, and then our B is this left shift, right? So what's happening here is we just write it the way we think we would, the way we write it in Python. We just write it all out on one line. We do 7 plus 8, then we times it by 3 shifted by 9. Or 7 plus 8 is A, 3 shifted by 9 is B, and then 7 plus, and then the multiplying of these two is whatever that C is, what that C operation was. So now what we would actually end up doing is we would fix that bug and get rid of these useless parentheses. So we're gonna write always FF, always flip flop. We're telling Vivado to infer these logics as flip flops because you don't want them to infer them as latches. And then we're gonna put at pos edge clock in. That means Vivado will go into this block of logic whenever we have a rising edge. We're programming that flip flop. We're like telling Vivado how we want that circuit to be wired by doing this. When you say always calm, you're telling Vivado, hey, assume all these variables are, Yabi, this wouldn't run. Okay, wait, hold on. Good. I was raised saying always use logics. Some people say wire and reg. Do what you want. I like having logics and explicitly declaring things. There might be some benefit to using logics over others. I might read a couple pages on it and make a video on that. Different topic. But yeah, so now what this is doing is this is literally just like pipelining it. We're saying, hey, put this computation into A, put this computation into B, and then into C, put the computations of A times B. What this non-blocking assignment does is it's saying, hey, put this into this flip-flop. So the data is not actually going to be available because the way flip-flops like just work is you won't see the data in the register till the next cycle. The reason that's really nice is because that's why this C isn't calculating like a straight line. It's not calculating using the current cycle's value. It's latching from the registers, which are referring to last cycle's values. Because on the next clock, that's when this current 7 plus 8 and 3 shifted by 9 actually get put into it. Yabi, these are constants. Yeah, I know. Imagine the variables. This is just for sake of showing. And assuming C is like our output, actually. There are a lot of holes in this. Okay. But yeah, that's pipelining. That's a quick code example. Now we are gonna figure out how to close this. Let's see if I can do that quickly. I cannot. Okay. And we're gonna get to our. I'm gonna keep this quick because I think my phone's gonna die soon, and it really sucks if I have to do a retake. So, today I'm gonna be talking about my dream 5-man lineup or 4-man lineup, counting me, on spotting aliens. So this lineup would be Barack Obama, Shaquille O'Neal, Bill Nye the Science Guy, and Zendaya. So, in my mind, if the aliens end up being hostile, this can be split into two completely different scenarios. But if the aliens end up being slightly more passive, Barack Obama would be very great at talking. You know, I don't think I'd be that good at talking in aliens. I'm not the best speaker. I go like Zeebas or Pee. But Obama, you can go like, "Hello, would you like baby back ribs with that?" You know, Shaquille O'Neal, just to keep the aliens in check, if they're thinking about attacking but they're on the fence, they'll see this super large human and think, no. Bill Nye the Science Guy, I don't know. Bill Nye the Science Guy and Zendaya are just sort of here for the hostile case. But yeah, so now there's the two cases. The first case is a Space Jam-esque 5v5 match against the aliens for the sake of the Earth. In this scenario, Barack Obama would be point guard, Shaquille O'Neal would be the 5, the center, Bill Nye would be the 2, the shooting guard, I'd be the 3, small forward, and Zendaya would be the 4, power forward. Barack Obama is a very clear choice for a shooting guard. I mean, not shooting guard, for a point guard. Let me just search up Barack Obama basketball. You'll see this position right here, textbook floater. You can't tell me he's going on. He's gonna. I can already see it. But see how he's shooting over them? See that rise he's getting off the ground? It's just amazing how many photos. Look at the hops there. He's basically feet off the ground. This is my point guard, and he's in the paint boxing out against. Okay. He's once again. If that's a lay, that's the lay I want on my point guard. Get past the defender, attack the rim. I'm gonna watch the Barack Obama. Shaquille O'Neal is the 5, incredibly obvious. And then Zendaya is the power forward. I just think Zendaya would be a good power forward. She's pretty tall, I think. I don't know. She's more for the other scenario, but I still think she'd be making a great power forward. Bill Nye the Science Guy as a shooting guard because he get straight scientific with it. I'd be at the 3 because I just feel like I should be the 3. I don't really like shooting threes. I don't think I'm big enough to be a 5-man against the aliens. I don't know if you ever watched Space Jam, but they put some crazy stuff, so no. The second scenario is I'm gonna get Zendaya off the screen. The second scenario is a Final Fantasy-esque 5v5 mage battle against the aliens. In this scenario, Shaquille O'Neal would be the tank. I'd be the main DPS. Obviously, if we had some mage-like battle, I'd get electric powers with daggers, and I'd go like zzz and get them. Barack Obama, secondary DPS, probably something to do with guns. Bill Nye the Science, because, like, president and military, not, yeah. Bill Nye the Science Guy, he could be like a Heimerdinger-esque engineer throwing bombs and potions at them. Zendaya would be our rogue. Bill Nye the Science Guy could also probably double as a healer, creating various potions to help out the team against the aliens. And then Zendaya would act as a roguelike. As most, I don't know if everyone knows, but like this Casey Undercover, she has spy experience, so I'm assuming that she has like the daggers holding them like the Vinland Saga way, like you're holding them backwards, and she's like cutting out underneath the legs to like weaken their ankles, and then they like shoot some attack in desperation, but Shaq is there like an iron shield. Shaq doesn't really get powers, he just gets like a hat, like one of them like them like hats with the spikes in it. That's all he really needs, and he's just a tank. I'm dishing out lightning attacks. Bill Nye the Science Guy in my rear throwing health potions, but also throwing explosives. And then Barack Obama as a ranged DPS. I'd be up front. I like daggers. Yeah, this is how we'd react against the aliens. Shout out this guy. He's a pretty close 6th man, but I don't think he didn't make the cut, sadly. I just don't really know if we need him on the court. Yeah, that's it. Next video, maybe just pipeline processors.